he'll be speaking, is Deni Salja, and his title is Persistent Diagrams as Change Action Derivatives.
Thank you very much. So yeah, thanks to all the organizers for organizing this and for giving me a chance to talk about this. This is a joint work with Christine Bauer as part of a USRA from last summer. And in the interest of time, I'm just gonna get to it. So first of all, in persistent homology, one usually studies nested sequences of simplicial complexes. So right here, so if you have that x is less than or equal to y, they're parameterized by the real numbers in this case. Then you have that the complex f of x is contained in the complex f of y. And usually you have some finiteness conditions on these things, like they only change at finitely many points in the domain. You can compute homology at every point in the real numbers and get this barcode or persistence diagram, which kind of summarizes the lifespans of the homology classes that show up throughout this filtration. If you take your coefficients in a PID, then this is a complete invariant, and there's a metric on these things, so people in TDA have found some really cool applications for them. Of course, there'd be more applications if instead of being parameterized by R, you could be parameterized by Rn, something a little more interesting. In that case, though, it's not really clear what lifespans are or what persistence diagrams are. So in 2019, in like June or so, McCleary and Patel proposed a solution to this in terms of something they called a birth-death sub-object or object. So in the case that you start with Rn and you skip past simplicial complexes and go straight to chain complexes in some abelian category, the finiteness conditions tell you that you're really looking at a functor out of a finite lattice into chain complexes. And you're mapping the arrows in the lattice to monomorphisms. You can talk about D cycles of F at X, F being this thing which was a filtration, quote unquote, before. And you can talk about D+1 boundaries at some other point Y, and you might ask, what are the cycles at one point X that are boundaries at some later point Y, to try to get to some notion of a lifespan of these things. All of these things are sub-objects of D cycles of a total complex, which these finiteness conditions exists rather. And that's denoted by this ZFD infinity. These things extend to functors, where the domain here is the open lattice, the topology on the lattice L being that of upper sets, which can be found over here. It's just generated by all the upper intervals. And yeah, you extend these D cycles and D+1 boundaries to these open sets by taking finite intersections of these things, since you started with a finite lattice. And these are pullbacks along the inclusions into the total cycle sub-object. Now for any two open sets, U and V, you can talk about what are the things, what are the cycles at U that are boundaries at V, by taking a pullback once again. And this leads pretty nicely to a functor out of the arrow category of that open lattice into sub-objects of the cycles of the total complex. So that's down here. And at this point, this is all McCleary and Patel's doing more or less. And they define a generalized persistence diagram as the Mobius inversion. Sorry, I should write this down. So this is Mobius inversions of the rank of the birth-death object. And then at a later point, they show that this Mobius inversion is actually the rank of some quotient object. In 2019, at the winter CMS meeting, Amit Patel talked about this, and he talked about how he saw Mobius inversions as a kind of derivative. So this made Christine and I think about finding a context in which we could see persistence diagrams as a kind of categorical derivative. And after looking for a while, we decided we wanted a categorical notion of finite differences to do this. So in order to make this kind of make sense, we need to extend the birth-depth subobject and the rank function. So first we extend the birth-depth object to this product here, where you're taking the arrow category of the open lattice times n op. And how you define this extension is you take the union of all the birth-depth subobjects over all of the iterated covers. And by iterated cover, I mean like things that came before. So if this is UV, then the first iterated cover would be like, or the first iterated covers would be all the things that came just before. The second would be all the things that came just before those. So we're kind of going down the down set, but keeping track of how many steps we've taken. And then if we let GA be the growth and D group of A and frac R its rank function, for every object, there's an induced functor out of the subobject lattice into the arrow category of the growth and D group, which is defined like so. So if you have a monomorphism from A to B, then the rank of B is the rank of the quotient B over A plus the rank of A, and that's what this square is telling us here. Okay, so how do we actually do this? Well, if we post-compose this extension of the birth-depth object with this extended rank functor, then that gives a functor from tau 1 op across n op into the arrow category of the growth and D group. And both of these things have something called a change action structure in cat. So what that means is there's a monoid that acts on each one respectively, like two different monoids. The monoid for the codomain is itself, and it works by pointwise addition or subtraction, just like an abelian group would act on itself. And on the domain, it's n op acting by addition in that variable. So there's a result that kind of comes from the calculus of finite differences in section 5.2 of LeMay and Alvarez-Bacallo's paper, Cartesian difference categories, which tells you that every function between the underlying sets of two abelian groups has something called a change action derivative, which is like a categorical finite difference operator. And this induces like a functorial version, where if you have a functor f from some category with a change action derivative to the arrow category of an abelian group, then it has a change action derivative. And there's actually a specific way that it's defined, which I haven't written here because it's a little bit long. Anyways, the point is that extending the birth-depth subobject, post-composing with that rank functor, gives you a setup like this. So by this functorial calculus of finite differences, it has a change action derivative in cat. And if you fix two of the variables at 0 and 1 in like the n cross n variables, that is, or n op cross n op, then you actually recover the rank of the quotient object in proposition 5.3 of McCleary and Patel's paper, which they showed to be equal to their definition of the persistence diagram. And that's this quotient object right here. And if you read what this is like this object here, this quotient, it's all of the things, all of the cycles at U that are boundaries by V, and then they're not cycles any time before U, time in quotations, and they're not boundaries at any point before V. So that means that they're cycles that appear at U and that are boundaries at V specifically. So we get a kind of notion of a lifespan being the set difference, U over V, or U take away V. So to summarize, you start with McCleary and Patel's birth-death subobject functor. You extended by taking unions over all these iterated covers. Then you post-compose with rank, and then this composite here is has a change action derivative given by this thing. And if you post-compose with an inclusion that fixes the two variables here, you recover the rank of the quotient object that McCleary and Patel defined. And that is what I have. Thank you.
Let's thank Deni. I was muted. Okay, any questions? Looks like Matthias has a question.
No, I was just clapping.
Oh, okay, that's the clapping, not the raise the hand. Sorry.
I guess I have a question.
Yes, direct.
Yeah, I'm just kind of broadly, I'm just wondering, do you think that there is further applications possible of either these kind of difference functors, or maybe for differentials as well? Should we be looking further into this type of category theory?
Yeah, I mean, when you think about derivatives in like calculus, you kind of define a derivative as this, as a limit of these kind of difference operators with some kind of normalization on the bottom, right? It's like Newton quotient that we think of.
Mm-hmm.
So one of the questions that I have might be kind of related to like, can you recover other like Cartesian differential structure as a limit of these Cartesian difference kind of derivatives? That would be pretty interesting, because in the change action derivative that you get here, you actually get a lot more information. I'm fixing two of the variables and saying this is the thing that McCleary and Patel really cared about. And that seems like you're kind of taking a kind of limit or something. So it'd be interesting to explore if that's the case there.
Thank you.
Other questions? Okay, so we have about